So welcome to the seminar today. So today our speaker is Nicolas Gheeraert from IIT Madras itself, and so he has joined us as a new actually he's probably the first international faculty, young international faculty of our department. So it will be a great pleasure to hear from him about coherent state expansion for simulating ultra strongly coupled systems in circuit quantum electrodynamics. Okay, over to you, Nicolas.
Thanks a lot for the introduction, Ian. So I'm very glad to be here to present my work. Right. So in this talk, I will be talking about my work on simulating the ultra strong coupling regime of quantum electrodynamics. So generally in QED, paradigmatic system would be a qubit coupled to an environment, to a bosonic environment. In the typical, in the standard quantum optics approach, the coupling is moderately strong. And generally, the qubit will only couple to a narrow line width of the environment. So it's basically to a good approximation, a single mode coupled to a qubit. And in this moderate coupling, there is also little correlation, negligible correlation with the environment. So what people do when they want to simulate the dynamics of such a qubit, they trace over the environment and they look at the dynamics of the qubit without really caring so much about what is happening to the environment. Now, when we reach a more stronger coupling, the ultra strong coupling regime, there the line width of the qubit becomes much larger. And in this regime, there are also correlations, even in the ground state, between the qubit and the bosonic environment, the bosonic band, right? So it's no longer possible to avoid looking and tracking every detail of what's happening in the environment. And obviously, it's a very large Hilbert space if one is to tackle that kind of system. And in this presentation, I'm going to show you how we can do that using basically by describing the quantum field state of the bosonic band using coherent state expansion. So by coherent state expansion, I mean instead of the Fock state basis. So we'll be using like a sort of coherent state basis instead of using the Fock state basis. So I'm going to explain to you exactly all this, how this all works. And so first, I'm going to motivate this approach by applying it to the rabi model to give you an intuition as to how my algorithm based on this coherent state expansion works. And then I'll move on to the key part of my talk, which is basically by applying this technique to the scattering of a coherent state on a qubit that is ultra strong coupled to a waveguide. So you'll see my motivation for this is it's also scattering is a very experimental feasible kind of protocol. And so I will show you basically in this regime that there are nonlinear effects that appear at this ultra strong coupling regime, and this is the kind of process, and I'll shed some light on the quantum processes that arise, nonlinear quantum processes that arise at this in this regime of strong coupling, ultra strong coupling. So just to motivate properly my work, I would like to start with a simple introduction starting from standard quantum optics. So when we talk about light matter interaction, we talk about light matter interaction. Fundamentally, there are two main fundamental processes that come to mind: the absorption of a photon by an atom that goes from the ground state to the excited state, and inversely. So when the energy of the a photon is that of the energy gap between the two levels, and there's emission when the an atom in the excited state emits one photon while relaxing to the ground state, which is termed spontaneous emission. So experimentally, they basically this to explore the physics of this light matter interaction at the single photon level. There are a few paradigmatic experiments So the paradigmatic experiment would be to use two mirrors, very high quality mirrors that can trap a single mode of the electromagnetic field. And we'd prepare, for example, the atom in the excited state, and then let it go through the mirror. And then as it travels during the mirror, the atom will progressively emit and then reabsorb successively the photon with the cavity. Therefore, if one wants to look at the probability of finding the atom in the excited state at any time during the travel of the atom in the cavity, you will see this kind of plot where the atom starts in the excited state, then goes to the ground state, and again, cyclically goes between ground and excited in a coherent manner. So these are where basically the first measurements of vacuum rabi oscillation by Brun and co-workers in the Serge Roche group. So obviously there's also another parameter. There's this decay of the cavity that is going, but because we're in a regime where basically the decay is much smaller than the other time scales, it doesn't appear in this time evolution. The reason that the oscillations decrease is because of other coherence losing phenomena like ionization of the qubit or dark counts and coupling to the environment. So these kind of experiments basically led to the Nobel Prize of 2012 to Serge Roche and David Wineland for groundbreaking experimental methods that enabled measuring and manipulation of individual quantum systems. Now, this is basically so. So this is what is called the strong coupling of cavity quantum electrodynamics, basically, which means that the coupling G between the atom and the cavity is much bigger than the losses, so that we can observe these coherent oscillations. But at the same time, it's not. It is only strong in the sense that G over delta is still smaller than 1. So delta here is, I remind you, is the difference of energy between the excited state and the ground state. So the coupling, let's say, the coupling is, in a sense, energy is much smaller than the energy gap difference between the two levels. So one can then ask questions: what would happen at stronger coupling, right? So at stronger coupling, you could imagine that there'll be enough energy, coupling energy, to lead to multi-photon processes, and so that this standard quantum optics picture would break down. Also, what would happen if we start coupling this atom not to a single cavity, but to many cavities at the same time, to many modes?
Nicholas, can I ask you a question?
Yeah, definitely.
So this coupling kappa, this is the coupling. This is the losses. I mean, this coupling is what? This coupling is the atom and the environment, or the light and the environment?
So kappa is the loss of the cavity into the environment.
Okay. Okay. Thank you.
It's coupling to the mode of the cavity. Kappa is the loss of the energy in the cavity in the environment.
Okay. Okay.
Right. So this would be basically the loss of the mirrors. The mirrors are not perfect; they leak some energy, so there'll be some absorption by the by the material or things like this.
Okay, thanks.
So now if we consider that there could be more modes coupled to the same qubit, that would lead to some kind of many-body nonlinear physics, right? And nonlinear, because of the strong coupling, could lead to maybe transfer frequency conversions and the such. So this is basically going to be more or less like the outline of my talk. So just to sum up, strong coupling with a single mode, that's the standard, that's what I told you before. Now, ultra strongly coupled with a single mode, that would be when the coupling is of the same order magnitude as the energy difference between the excited state and the ground state. And then we would define multimode ultra-strong coupling regime, where because here there's no, there would be no single digit, there'd be a coupling to every single mode of the multimode environment. So here we have to look at gamma, the relaxation rate of the QED into the environment, right? And so when this gamma over delta is of the order of 1, we are in the ultra-strong, so-called ultra-strong coupling regime. So in 1D vacuum, you would be able to make this approximation where this relaxation rate, it would be a fine structure constant times the qubit energy excited minus ground state energy. So then you would write it this way: alpha, meaning this fine structure constant of the order 1. So obviously in vacuum, this is only for vacuum. Now we have to find a way to actually tweak this effective. Obviously, we will not change the fine structure constant, but we'll change the effective fine structure constant. And yeah, so that is what we'll have to do. So right, so this was standard quantum optics. And now I will move on to tell you exactly how we can reach the ultra-strong coupling regime with a single cavity mode. Yeah, right. So just to remind you quickly, and give some, so yeah, so the quantization for a mechanical oscillator would be given basically for a mechanical oscillator, we'd have a Hamiltonian equal to p squared over 2m between p and x, and the commutational relation would be between x and p and given by I h bar. And if we apply this, that would lead to basically quantization, which are called phonons. Now, if we look at light, basically this time the commutation relations are between the vector potential and the electric field. And when we quantize light, we get photons. So we can do the same with an LC oscillator, where basically there'll be, we have a capacitance and an inductance. In this case, we'd find commutation relations between Q and phi. Okay. Just 1 second. Just 10 seconds. So,
okay.
Right. So I was talking about the LC oscillator. So here, so that would be, again, a harmonic oscillator. And here we would find a quantization between the charge and the flux. And that would be IH bar. And that would lead to something called plasmons, basically quantization of oscillations in this system. No, obviously, there's no real difference fundamentally between the LC oscillator and the electromagnetic environment. But generally, that is how we start quantizing the system. We quantize the system in terms of starting from a lumped element system.
So for the photon, you're using the Coulomb gauge, I suppose.
Yeah, that would be the Coulomb gauge. Right. So so here is how we can create our bosons. So with light, there would be right. So here what we're going to do is basically we're going to use electrical circuits using an LC oscillator to create the bosons of our operator. Right. So how do we fabricate this kind of system experimentally? So in this kind of systems, we basically have a silicon chip which is gold plated on one side. And so an inductor can be created, for example, by creating meanders on the silicon chip. And the capacitor would basically just be like two capacitor plates, and that would create a simple LC oscillator. Now in practice, we use, even for a resonator for inductance, we would use Josephson junction. But in this particular system, that's a good enough example. So that would be our LC oscillator. So now, obviously, if we want to be able to control plasmons, if we want to control quantas, this kind of system, we have to make sure that the thermal temperature is much lower than the energy of these quanta. So that means that we have to go to a frequency that is lower than 5 gigahertz, equivalent to 250 millikelvin. So that would be the right. So we'd have to lower the temperature. So generally we lower the temperature to 20 millikelvins, just in order to be much lower than the thermal energy of the phonons at this frequency. So right. So then, so now we have basically a bosonic mode. Now we need the qubit to interact with this system. So how do we create an atom, an artificial atom, using a superconducting qubit? So one way of creating a superconducting qubit would be to create a Cooper pair box, and that is basically where we control two different states with a different number of Cooper pairs on an island. So here again, this would be like a schematic of a chip. Here we have a superconducting island with connected by a Josephson junction to the rest of the to the rest of the system, right? So there would be two possible states. Let's say there would be like N0 Cooper pairs plus 1, or two N0 Cooper pairs plus 2. In that basically Josephson junction here would basically just be a tunnel barrier. So the Hamiltonian for such a system would basically be a charging Hamiltonian, and so a tunnel Hamiltonian, where basically delta would be like the superconducting gap, and EJ, and then so that would be just the hopping term between the n+1 number of Cooper pairs and n Cooper pairs. That would be the tunneling Hamiltonian, and the charging Hamiltonian, where basically the size of this island is going to be given by this mostly by this EC, this charging energy. And there's also here, as you can see, there's a bias potential VG that is going to be allow us to tune to basically tune the degeneracy energy. So in particular, if we tune VG to be this quantity there, CGVG over 2E, to be exactly 1/2, then we'd all be able to get two quantum state. One would be the superposition of N0 plus 1 and N0 plus 2, and the ground state would be N0 plus 1 minus N0 plus 2. And these would be our ground state and excited states for this system. Right. Okay. So now we have defined our, our states. So this is our subspace, and so if EC is large enough, this charging energy is high enough, we'll locate the system in the subspace N0 plus 1 and N0 plus 2. Won't be able to go to other states, and we'll define.
Can I ask a question?
Yeah.
How is this tuning done? I mean, it's rather delicate to get it to half.
So I think it's basically this is done using a DC line, and one can actually have enough accuracy, I think, to just reach the half point. So how do we actually reach 1/2?
Yeah, how do we know we are at 1/2?
Okay, how do we know we're at 1/2? Right. So
if you don't know the answer, it's okay. I mean, because it's some experiment.
So Hi, Suresh.
Hi, Balaji.
Yeah, I can quickly try to answer that. So if we have a squid loop, which is two Josephson junctions in parallel, by setting an external magnetic flux threading the loop, you can vary the Josephson energy. So Nicholas, the delta that you showed in the previous slide was the Josephson energy, right? It's not the superconducting gap.
Yes, correct. Sorry. This is EJ. That's what I tried to
That
correct.
should be, yeah, it should be EJ there. Yeah. So by changing the magnetic flux threading the loop of those formed by the two Josephson junctions, you can change the transition energy of this artificial atom. And you usually control this, or you fine tune it by mapping out the transition energy as a function of EJ in spectroscopy experiments. And then it's relatively robust once you characterize it. Does that answer your question, Suresh?
Yeah, it does. Thank you.
Yeah.
Okay. So this was mostly to get the formalism there. So we would define the upstate as being n0 plus 1 and the downstate of our effective two-level spin as being n0 plus 2. And that can be written as a sigma x operator. So that would be the qubit itself. And so now for the resonator, it would simply be annihilation and bosonic and annihilation operators. So the standard A dagger A Hamiltonian. So now we can put them together. We can put this harmonic oscillator with the Cooper box, and with the coupling capacitance between the two. And so this coupling capacitance is going to lead to the coupling between the different between the bosonic mode and the qubit. So that would be strictly equivalent to this standard quantum optics picture where we have the cavity in an atom in vacuum. Except this time, you can see that the coupling is going to can be tuned by this capacitance. So we effectively have a way of tuning the fine structure constant in the context of this electrical circuit. So that's this cavity QED, and this would be termed circuit QED. So just for history, the qubit in 2010, Niemczyk and co-workers managed to reach a ratio of G over delta of the order of 0.23. And finally, in 2017, G over delta was, Yoshihara and co-workers reached G over delta, the order 1, so deep into the ultra-strong coupling regime. So and so this leads basically to what is called the rabi model, where here in the middle we have this coupling term between the sigma z operator and A dagger plus A. That was G, and G is a constant. So this is the rabi model. Now so I would like to, so in order to move on to tell you exactly how this coherent state technique works, I would like to start from a very concrete example of what is happening in the system, of a concrete dynamic. So my collaborators on this work were Serge Florent and Shomo Vera, who was a postdoc in our department at Nel Institute in CNRS. In Duke University, we have collaborators, Harold Verangen and Xin Zhang. And finally, we had also experimental collaborators working on the experimental implementation, which I'll show later, Nicolas Gheeraert and his PhD student Javier. So basically, when we look at the rabi model, we can try to prepare the system in the excited state, in the upstate, with 0 bosons in the harmonic oscillator. So if you look at the time evolution, you prepare with the moderate coupling, G equals 0.1, the energy gap of the qubit, you would see that the qubit starts oscillating between the up state and the down state. This would be just like, this would just be a precession on the equator of law sphere. Because I am not starting in the excited state, I'm starting in the polarized state, sigma x. Now, if you increase the coupling to G equals 8 times the energy gap, you'll see that the some much more exotic behavior, where the qubit starts to a tunnel for a short period of time and then reaches a plateau. And again, it's this tunneling resumes and again reaches a plateau. So to understand what is going on here in this dynamics, we have to look at what's going on in the field state. And so for that, I'll prepare I can expand the state vector in terms of a field state and the up sector, and a down field state in the down sector.
So Nicolas, I have a quick question here. So you are considering an abstract two-level system, right? Not a transmon or any such multi-level system for the simulation.
So I'm actually assuming a Cooper pair box.
Okay, a Cooper pair box. So practically a two-level system.
Exactly, practically a two-level system. Even though this is not exactly these days not what people would in fact use transmons.
Okay.
For this particular system, I'm only considering a Cooper pair box. Right.
Okay. Thanks.
So I'm defining a Husserl Q function, which is basically the projection of the field states on a coherent state beta. Right. And so if you look at the time evolution, so here on the left, this is the field state of which is in a direct product state with the up state, and this is the field on the right is the field state when the qubit is in down state. So initially I started in the up state, right? So all the probability is in the up state. Now, you see, as soon as the time evolution starts, there'll be a tunneling from the up state to the down state. But as soon as these two field states become orthogonal, you see that it reaches a plateau. The tunneling basically is killed. And as soon as they, again, the entanglement is lost between the two, you see that the tunneling resumes. Right? So you get this cycle. When they overlap, the two overlap, you get tunneling. When you don't, basically, you get a plateau. Right. So now, what is interesting here is you can see that we are reaching this final state, which still has basically looks very much like part of it looks very much like a coherent state. This big blob over here. So the motivation would be to see whether we can describe this field state using a superposition of coherent states. So obviously we would not be able to just add them this way. We have to add some weights, and we'd have to expand basically this field state in terms of a superposition of coherent states in this manner. Right. So let me just skip the.
So Nicolas, what's the motivation of expansion in coherent states?
So the idea is later on, this is going to, right now, this is all basically diagonalizable. So all what I'm showing here is nothing new. But when we start looking at more modes and multimodes, this is going, there's going to be a huge, huge advantage. Basically, if you look at, okay, at a certain power, you won't be able to track all the degrees of all the states of the system. So let's say, for example, if you have 500 photons in your system, you won't be able to diagonalize the Hamiltonian to obtain your states, right? Your eigenstates. So if you use a coherent state, then you only need to look at the particular the dynamics of the particular coherent state moving in phase space. So you'll have an adaptive basis where the coherent state is moving. And basically, this is very efficient in terms of solving this system. So I'm going to...
Nicolas, there is just one question. So suppose if you could also motivate the coherent states more naturally in the sense that, okay, this is a very nice motivation that you have given, but if you just have a constant field coupling to A plus A dagger, a classical field,
Right.
And this with this PDAG array, your system, if you start from the vacuum, you should go to a coherent state. That's at long time you will reach the coherent state, which is determined by this. So now you have instead of a constant field, you have a quantum operator.
Right.
But then you would suddenly think about as the coherent state basis should be the most natural kind of expansion basis, right?
Right. Exactly. It would be the more natural basis. And here, see, I could also show you the Hamiltonian. So you can see that if sigma z is 1 or 0, you know, plus 1 or minus 1, you can see that then when you apply suppose you forget about omega and delta, when you apply the time evolution operator, exponential of minus IH,
right?
That this would
get two different coherent states. Yeah,
you would get exactly the basically a displacement operator to create the oscillator. So you can see it from here.
Exactly.
Yeah. So if you only have this term, the middle coupling term, and you forget the other terms with no tunneling, then that would actually be only one coherent state in both sectors would be enough to describe the system. But you have to.
Yeah, and there would be two different. Yeah, exactly. It's depending on the value of sigma z, you will get two different coherent states. Yeah. And exactly, good.
Exactly. And the sigma z will complicate the picture, of course.
Will complicate the picture.
This is what I showed you with the tunneling the two sectors of the yeah.
Yeah. Okay. Got it.
So that is there. Okay. So just wanted this just the definition of the harmonic oscillator. We'll just skip that. So harmonic, this is a coherent state, which is defined by. I'm just skipping the animations, which is defined by this displacement operator, displayed by beta in phase space. All right, so that is the definition, basic definition.
So, Nicholas, in your previous slide, what decides the time scale of this plateau?
Right. Basically, yeah. So I believe that would be the frequency of omega. So if omega basically is basically, so omega would be the frequency of rotation, right?
Yeah.
So if omega is very slow, then I guess it would take a lot of time for the states in the up sector and down sector to superpose once again. Whereas if you get fast oscillations, basically they would be oscillating at a higher, a faster rate. Does that make sense? I think this oscillation here is given by omega mostly. This basically this.
Sorry, can you remind me what exactly is omega?
Omega would be the frequency of the harmonic oscillator in the system.
Okay. Omega is the frequency of the harmonic oscillator.
Right.
Okay.
So right. So one is displaced to the right because the qubit is in the excited state, and the other is displaced in the other direction because that would be the down state of the qubit, and then as it is displaced, then it starts precessing in phase space because of this omega. So I think this omega would basically define how fast it's coming back to the center. And if it's in the center, then basically there's no entanglement, right? So as soon as there's entanglement between the qubit and the environment, then we lose the tunneling. It's as if the qubit had been measured by the environment. And as soon as the environment becomes a product state again, I mean, as soon as the environment is in the middle, we have no more information. The environment doesn't possess any more information about the qubit state. So it's as if the measurement, the measurement was erased. That's, I think, one way you can see it. That basically this displacement in phase space creates a measurement by the environment, and then this is erased as the field states are recombined. I don't know if this makes sense.
I see. Just to clear, so Nicola, you are using field and environment interchangeably, is it?
Right. The field state. I mean, yes.
Okay, that's a bit confusing to me. Okay, now it's clear. Okay.
Yeah, because there's only one harmonic system in this system.
Right.
That would be the harmonic oscillator, which is described by a field state, quantum field. right?
Okay.
So that's why I mean the quantum field state would be the field state of the harmonic oscillator. Yes, I'm maybe using them a bit to interpret.
Okay, thanks.
Right. So, right. So now, right. Okay. Sorry. Yes.
Hi, could you just remind me what are the respective roles of the LC oscillator and the Cooper pair, the Cooper box? Is
So,
one the environment and the other the?
yeah, so in some sense, yes, that is true. What I mean by environment is by this cavity mode. And the reason I call it environment is because I'm already seeing the next part, the key idea, the key point of my talk, which is coming later, where I'm actually using multimode environment, which is a continuum basically. So you can see it as a bath in an environment. So here, yeah, the cavity, you cannot necessarily call it I mean, I'm just calling it an environment in.
Right. So that's the LC oscillator, right?
Exactly. The LC oscillator is the environment.
Okay.
The environment.
Great.
And qubit is basically, yes, the two-level system.
Okay, thank you.
But yeah, good point. I'm interchanging nomenclature very fast. Way too fast. So, right. So the idea is, if you had to, this is the proper motivation for the coherent state. So if I had to expand in terms of Fock states, I would expand, most general expansion would look like this. Basically a superposition of Fock states and Fock states for the up sector and superposition of n Foxes for the down state. So that would be a most general expansion. Now our idea is to actually expand in terms of coherent states. So now we have these weights PM and FM are the coherent states in the up sector, and QM the weights, and HM the displacements in the down sector. So right. So that is that. So that would be in NCS. The size of the expansion is basically only what is necessary in order to properly describe the field state. So then we can define a Lagrangian for the system given by the. Yes.
Hi, sorry. Maybe I just don't understand something. Why are there two sets of coherent states?
Because you need to be able to account for entanglement between the upstate and the downstate. So the most general, so in the same way as when you expand in terms of Fock states, you would need to be able to have a completely independent down sector for the field state and an independent up sector, right?
No, but I thought the up state and the down state, right? I mean, there are two states of the same system, or they're.
So there are two states of the qubit, the up state and the down state,
Yeah.
right? And then these down states. See, if they are not entangled, then indeed we only need one set of Fock states, and that could be in the one expansion in terms of Fock states would give us the one field state of the system. Now, if there's entanglement between the upstate and the downstate, there can be a different polarization of the field for the upstate and different polarization for the downstate. Then you would get an entangled system, right?
I guess I'm not understanding
I think the confusion is arising because I think what he's saying basically is the field state of the oscillator is entangled with the qubit state.
Oh, okay.
Yeah, and you have a basis of coherent states for expansion when the qubit is in the excited state, and there is another set of coherent states when the qubit is in the ground state, and these two joint states are entangled, and he's writing a generic form for that.
Okay. I see.
Also, thanks. Why F and H are different? Okay, that is also because in this case, now F and M and H are variables, so the displacements are also variables. We have an adaptative basis because we don't want to describe the full state, the full field state. That is actually the idea. So now we will have our basis is going to move with the time evolution.
Mm-hmm.
And that
right.
different
Right. Okay.
quantum
Okay.
states in
Got
the
it. Thanks.
sector. Right. So right. So now that is the important difference. Now we have the weights that we have to of which we have to look for. We have to solve in time. But we also have the displacements of the current state that we have to solve in time. So that is what we do. We use this Lagrangian to define that, and then we use an adaptative Runge-Kutta for kind of algorithm to evolve in time. Right. So just to demonstrate, the effectiveness, of the technique, here I'm looking at the time evolution. So again, I'm looking at this example that I reviewed before, except this one, this is the up sector. This is using my technique on the left, using the multi-coherent state expansion. And this on the right is just a direct diagonalization in terms of Fock states, using Fortran. So you can see that and this is after 20 of time. Okay, so I've chosen these parameters g equals 4, delta equals 1, omega equals 1, and after t equals 20 of time, we obtain this field state for the up sector. And so you can see, first of all, that the distribution is very, very close. And here in white, I've shown you where the coherent states are actually located, right? So we have 7 coherent states. They're located at different parts, and because of the different weights that they have, they actually are able to reproduce exactly this field state. So in that sense, it's a very efficient way of looking at the system, because here we had to look, at a very large Hilbert space with many, many photons, possible photon states, going to 100 possible photons. Here we only have 7 coherent states.
So Nicolas, the coherent state space is actually a continuum, right? Unlike the Fock state space. So on what basis do we say 7 coherent states?
Right. Okay. So the idea, so yeah, as you say, the basis would be, the idea is this Glauber-Sudarshan kind of expansion where any field state can be expanded in basically an integral over coherent states, right?
Correct.
Right. Now, what we are doing here is we're using only a subset of this expansion by using only the coherent states that we need. And to compensate for the fact that we're not looking at the full space, we're not using all the current states of the Glauber-Sudarshan expansion. Basically, we're only choosing the ones that are needed to basically.
So it's a numerical approximation that you're doing in terms of a summation.
Exactly. So now I will add more current states if I want even more precision. Right.
Okay.
So exactly what I would have shown, I will show you like in the next slide quickly. So here I just wanted to show you how it works when I'm doing the full dynamics of the system. So now I'm just showing you the same video as before, except this time. Now I'm going to show you with white dots exactly where the coherent states are during the time evolution. Okay. So again, these are the Hosemi-Q functions for the up sector and down sector. And right, you can see there's one main coherent state over here, and these coherent states are moving, right? The displacements are moving. And the small ones are basically low weight coherent states that are here just to describe the tail. I've described them using a small point. And over there, you can see also that the trail in the down sector is also described by many coherent states. So even in the dark areas, you can see that there are some small coherent states. And
sorry, I have a basic question. So a priori, you would not know, because if you look at the full time evolution to know which points in the coherent state space would get maximum weightage. So you have to keep all of those. Right. So so you don't know a priori before you run the simulation which these points are going to be. So how do you decide?
Right. So basically, it's the it is the algorithm. It's the time-dependent variational principle based on this Lagrangian that I showed you before that is going to basically define the time evolution of the displacements of the coherent states and the weights of each of these coherent states. So what happens?
How does this algorithm work?
Right.
So what is this?
Right. So initially, I would basically, at the beginning of the time evolution, there's only one coherent state. So I start with only one coherent state in my expansion. So the initial state is actually very simple. You would forget about this sum, and there would be only one F here and one H for the down sector. And here you would have P of the order 1 because we start in the excited state. And basically, then I can define an error that is going to tell me exactly, there's an error, basically the deviation from the Schrodinger equation that is going to tell me exactly when the error the error starts to increase. And when this error starts to increase, then I know that I need to broaden my state expansion in order to be able to describe the phases accurately. Otherwise, I would basically get only an approximation, a very rough approximation. So as soon as it starts, you can see that here they're added basically in the time. So I'm broadening.
Oh, so you can add by hand as we evolve in time, more and more.
Exactly. As soon as
I see.
Calculated error, it goes above a certain threshold. My algorithm will add a current state. You can add a current state because you just
but I don't understand how this is compatible with the Lagrangian method, because usually when you talk about Lagrangian method, you declare your variables once and for all, but you don't keep adding variables to the system.
Well, actually, you can, yeah, I see what you mean. But in practice, you can still add variables because you just have to add in this expansion that you can see here, that PM, FM, you can add an additional coherent state with 0 displacement and 0 weight. So that 0 weight coherent state that you're adding in the expansion is not having any effect on your state vector, right? However, as soon as you resume it, so I would stop the time evolution. I will add in my array of coherent states, I will add one more element in that array, and as soon as I restart the time evolution, then it is this time-dependent variational principle that is going to take use that coherent state if it needs it.
I understand, but I understand what you're saying. But the problem is that suppose you have a set of nonlinear equations, and in some time, there's 16 variables. At some time, say a subset of the variables are large and some are small. At other times, other subset are large and other small. So in that case, if you keep ignoring something, wouldn't it lead to some kind of inconsistency in the sense that
ignoring what?
Because all of these are coupled, and you might think that ignoring this would give small, but it can at some late time you might get large errors because you ignored. Because errors can accumulate over time, because all the variables that you're taking, some of them are large at some time and some of them are small at some time. Right. Now, if you ignore the small variables at some point of time, you can accumulate large errors at some later
time. But okay, see, the thing is, initially, the error would be very low. So I would know that I'm not missing on any degrees of freedom.
Initially low, but you have a time evolution in the system. And how do you know the errors are in control always even at larger times?
Yeah, because I can calculate that error. So let me show you exactly how I calculate this error. I'm showing that in the next slide. So this is basically like a convergence kind of plots. So the same kind of system, and I'm looking at a convergent plot of the sigma Z system. If you remember, I had shown you these plateaus, right, already before. So this is until time 40. And this is with these are the plots with different coherent states. So with only one coherent state, you only get plateaus. And in fact, if you look at the expansion, it's very easy to understand that that these would actually give rise to plateaus if you try to describe each sector by a single coherent state. As soon as you increase the number of coherent states, slowly you start to converge the system at small times. And you see with 8 coherent states, you are able to, so in dots, I have the exact diagonalization, okay? So these dots are actually the exact solution, the black dots. And with 8 coherent states, I'm able to reproduce exactly this time evolution. So for that, how do I calculate this error? How do I know when I have to add this coherent states? So this error, I'm going to define it as, I'm going to define a ket state, which is basically the deviation from the Schrodinger equation. So it's IDT minus H. So instead of having IDT equals H psi, IDT psi equals H psi, I take it to the other side and I define this ket state. Okay. Now this error is then going to, I define an error as a norm of that ket state. That gives me the error, the dynamical error of my system. And you can see, and thus I'm plotting this error over here in terms of time. And this is the error on the y-axis. And you can see that at 0, it increases. And then I add a coherent state. You can see this error goes back to 0. And then it increases again. And then again, here I'm adding another coherent state. Here are the 8 coherent states that I've added in the system. at every peak. Okay, so you just define this error max, this threshold at which you think that this, depending on what accuracy you want in your simulation, and at this error max, you decide that there'll be an additional current state, so the system will provide more accurate dynamics. The simulation will provide you with more accurate solution. Okay, I don't know if that's clear.
Well, I still have some issues with this way of thinking, because in principle, maybe I'm wrong about it, but in principle, you can have some overlap with some states which doesn't contribute to the norm. But for example, you can have some overlap with some orthogonal state,
right,
which doesn't contribute to the norm.
Right, but
so that doesn't mean that you have approximated.
But if so, I don't know if I'm wrong, but if there is an overlap between with an honest state, wasn't that?
Okay, I see. You're taking the full norm. I see. Wait, yeah, I'm still a little confused by this. I'm not sure if that is the right.
Okay, so the expansion or the error that I've
of the error itself, I'm a bit confused.
Okay, so but you agree that this IDT minus H would have to be 0.
Okay.
We have basically a perfect. If our dynamics is perfect, then this should be 0, because then that would mean that psi is our solution, right? Psi is the solution. So then if this psi should verify the Schrodinger equation, and therefore IDT minus H psi should just be null. If we have if our solution psi is actually accurate. Now, when it's not accurate, it's not accurate because it's only a partial expansion. It is going to give an error, and then just to get a real quantity that we can look at, I'm looking at the norm of that state, and then that gives us basically if this is 0, we know that our solution verifies the Schrodinger equation. If this is not 0, then we know that there's an error, and therefore, we know that this is due to the only to our ansatz being too small, because that is the only possible source of error in this kind of thing. Of course, there's also dynamic with time step and everything, but that I do take into account. That there are other ways for this, right? So I know I'll use a small enough time step to know that this is with this.
Okay, I see.
So this is really an error that will define how far our basically ansatz is deviating from the actual solution.
Okay.
So you can see here, I went even to 16 coherent states. You can see it keeps decreasing this error. So here I've chosen a particular time step, a time t delta equals 6, okay, or somewhere over here, and I'm looking at how the accuracy increases. So there I can go to 10 to the minus 5. In terms of error. So right. Okay, so this is basically the idea. Hopefully, I'll have some.
So essentially, you are saying that once you choose a basis of coherent states, essentially your Schrodinger equation would reduce to some Lagrangian system, or which are these variables PM and QM. That's of course that's the thing that you are claiming. And is it, am I understanding correctly?
I didn't hear properly.
Sorry, so the claim is that you're short. Once you write this answers for the state, that if you include a finite set of this coherent states, tensor products with this up and down, then your Schrodinger equation reduces to a set of Lagrangian equations for this evolution of this PMQM. Right, that's
right. So it's actually one Lagrangian, but then Lagrange Euler equations. Yes.
Okay. So you can write it in some sort of Lagrangian
for all the variables of the system, and right, exactly. So then I have to solve this system of equations. To obtain time dynamics. Every time steps, I'm solving these Lagrange Euler equations.
But is there also some there should be also a path integral way of formulating the problem, right? This is because you could do it naturally on coherent. You can do a coherent state path integral, and for the qubit you can also do it on the sphere. So you could convert, I think that you can also write coherent states for the qubit if you want, or in some, or maybe just don't want to do it, but is it some, so it seems to be a very natural thing to say that you're, in some limit, it's like you're taking some approximation where it is like a saddle point on the path integral, or a saddle, some very on this coherent state path integral, and then there are small fluctuations maybe on top of it. So if you're so natural, so if you so what I'm trying to say that is there some way to understand it using this path integral way that so maybe what you're saying is that at some point you have some larger fluctuations around this path, and at some point you have smaller fluctuations around this.
Smaller. Okay. Okay. Around the path of a single coherent state, you're saying?
Yeah. So suppose think of it as a path integral on the coherent state basis, then you get some kind of path which is a solution of your Lagrange system. Right. And then the fact that you need some more things, it means that you have some weight, some fluctuations around this classical path. Right. At some points more and some other times less. Yeah. Just to get a bit better physical interpretation of
I think
physical understanding.
That might work in some cases, but not sure in the general case, because when you look at a very complex states where you have basically a very dilute, diffuse kind of probability distribution, you actually get high weight coherent states everywhere in the field, in the in the phase space. So there you can't really say that there's one major coherent state and there are contributions, small contributions coming close to it. So that might work in some cases, especially when we have a one coherent state and a trail, like similarly to this I was showing, where you have a trail following the main coherent state. But I'm not sure about the general case, because this idea that one main coherent state is there would probably not be correct.
Okay, nice. Okay, thanks.
So just let me know how much more time I would have. I would like to show you.
How much time you need? You have 5 more minutes officially, but you can take maybe 10 more minutes, 10 or some more. Is it fine, or you need more time?
That is fine. I mean, so I can cut on a few parts maybe. So okay. So I wanted maybe, should I skip on the experimental motivation, or would you like to hear about the experimental motivation?
I would.
Okay, very well. So this system, this is a system that was basically on which Nicolas Gheeraert is working at the Institute with Javier Portat Martinez. So you can see this is actually the SEM image of the chip, where we have a qubit here on the left. So there's a Josephson junction in the middle with huge capacitor pads. In here, we have a long chain of Josephson junctions. So this there are 5,000 junctions coupled one to another. So this lead gives rise to normal modes, and this continuum of normal modes is going to interact with the qubit. So now we have a multi-mode environment. Instead of a single harmonic oscillator, we have like a continuum of harmonic oscillators with different frequencies coupled to this qubit. And we are reaching the onset of the ultrastrong coupling, let's say, mainly because of this capacitor coupling, but also because this is a very high inductance transmission line, which uses Josephson junctions. So this high inductance and this capacitance gives rise to a very strong coupling. As a circuit, we can write it this way. Here we have this transmon qubit coupled to a long chain of harmonic oscillators. This is the motivation. Of course, my simulations are still for a pure two-level system, so I'm not considering the extra levels of this transmon. Right. But so again, just to give you some motivation about, how big is the Hilbert space, if you had to solve this kind of system using Fock states, then you'd need to account for all the possible photon occupations of every mode, right? So that would give rise to if there's 1,000 modes and you want to look for possible occupancy of 5 photons in each mode, that would always be 10 to the 15th states. Clearly very difficult computationally. Now with a multimode approach, we can start defining multimode coherent states with going from K1 to Kn, the 1000. And so, right, so what I mean by this state, right, this is basically a product state of a coherent state for every mode of this environment. Okay, so now this is a much bigger system. I need one displacement for every mode in the system. So that would be what I would call one coherent state. This product states of coherent states, right? M is the index of the coherent state. K1 is the index of the mode. Right. So the dynamic Hamiltonian can be written in terms of charge variables and phase variables. And this is the cost. This is basically the energy of the Josephson junction, and so it happens only for a Cooper pair box, and that can be basically mapped to the spin boson model, where basically so what we have here the qubit energy again, except so same thing as the rabi model, except this time we have a continuum of modes k that are coupled to the sigma z of the qubit, right? And now the energy of the harmonic, the environment is basically a superposition, basically a sum of all the omega k, dagger k, ak. So that's the spin boson model. And this is what I want to look at. So, okay, I'm going to skip this part. These are the quench dynamics. We can talk about it later. We define the error in the same way as I told you before. We can see that the error in this kind of system converges. Okay, that might be a bit fast, but let's move to the scattering protocol. So now, basically, we have a continuum of modes. So this is basically we have so that's basically constitutes a waveguide. So the continuum of modes is a waveguide to which the qubit here is coupled. Now, because of the ultrastrong coupling, in fact, there will be a polarization cloud that will form around the qubit that will be given also by a superposition of coherent state, be a complicated entangled state. That's what I've depicted using a green cloud, right? So that would be the polarization cloud around the qubit. Now, my protocol is basically simple. I basically prepare a coherent state left of the qubit. So that's very easy to prepare because I have already, I'm using a coherent state basis. So I'm just going to define one coherent state here with a certain mean number of photon n, a wave mean k0 momentum, and a certain line width. So that's how my initial state looks like. I have a coherent state, which which the displacement, multimode displacement, I've named Z, and this ground state is basically this state here in the middle. So that would be the complicated qubit environment kind of ground state. So what I do, then I do the dynamics of the system. This coherent state is going to move right. It's going to scatter on this qubit, and I'm going to obtain a scattered wave packet and a reflected wave packet, right? But now the outgoing wave packet is no longer a simple coherent state. There have been nonlinear processes that happened. So this outgoing coherent state, the outgoing radiation is going to be also a superposition of, sorry, I wanted to, okay. So the outgoing wave packet is also going to be a superposition of coherent states, basically, because we have to account for the nonlinear processes that happened. Therefore, these are more complicated than just classical states. They're now completely quantum states. So the qubit relaxes to the ground state. That's why it is at the end of the dynamics, we are back to a ground state in product state with the outgoing radiation. Right. So right. I'm still audible, right? Just want to be clear. Is that my protocol?
Yeah. Okay.
So no, I'm just asking because from the previous presentation, I had had an experience where my connection had broken down in the middle. So so here then I'm looking at the spectrum of this outgoing radiation. So I've only chosen one particular initial k, a momentum, right, of this incoming wave packet. And now I'm looking at Fourier transforming basically this outgoing radiation, and I'm plotting the mean number of photons for each mode in this outgoing radiation. Okay, so here on the right I have right-going modes. On the left I have negative K, which is left-going modes. So you can see that I've shown it with delta R. This is basically the resonance of the qubit. Okay, and so the initial K0 that I've chosen with dashes over here is actually off resonant, but because of the ultra strong coupling, there's still a small amount that is reflected, even though we are well off of the resonance, right, at the frequency at which we are sending the radiation. So this is the transmitted, this is the reflected wave packet. Okay, and to actually see what is happening, the interesting part here is actually here at the bottom of these peaks. So we have to zoom in. So now I'm zooming in really at the bottom of these peaks, and you can see that here, apart from these elastic peaks, we have a large inelastic spectrum here over there, especially in the middle, and here on the right, these little lobes, satellite lobes on the edges, right? So then we can convert this coherent state expansion, right? So I've told you these outgoing radiation is a complicated quantum state, so it's a superposition of coherent states as solved by my algorithm that I described previously. But I can also re-expand this state generically in terms of Fock states, right? So there would be like alpha k, the amplitude for having one photon states with momentum k, then alpha k1 k2 be the amplitude for two photon states with k1 k2, okay, etc., etc. So using these two, I can basically do a little bit of arithmetics and get to the probability amplitude of getting the Fock states, the multimode Fock states, right? So I mean the multi-photon amplitudes, which is given by this expression in terms of the Fox, my coherent state degrees of freedom. So then now that I have the probability amplitudes of all these Fock states, of all these four multi-photon states, I can plot that here so I can plot the two photon states, right? And I can plot the 3 photon states. This is going to be here, and the 4 photon states are going to be here. Okay, so if you add all of these, you get back to the total number of photon, total cross section that I showed here in gray. Okay, so then we can start trying to understand what is happening exactly. So basically, if you look at at the plot of the probability of the two photons in terms of the momentum of the first photon, momentum of the second photon. So I'm looking at the blue curve, the two photon curve, but this time I'm plotting it in 2D because there are two momenta, right? So here in this negative quadrant, we get the reflected peak minus k0 minus k0, and this would be the elastic peak that is transmitted plus k0 plus k0. We also have these satellites. In this satellite basically is one photon. You can see there's one photon emitted at the delta r, the renormalized qubit frequency, and the other photon is renormalized at 2k0, 2 times the energy of the incoming photon minus delta r, according to conservation of energy. So you can see that this is basically this process, which would be 2 incoming k0 and these 2 outgoing photons, and this is what is so-called an RWA, a rotating wave process, in the sense that this only accounts for the rotating wave terms. This also appears with the rotating wave terms of the Hamiltonian. Now, if you look at this 3 photon curve, however, so this big inelastic spectrum in the middle, so you will see that here, so here we cannot make a 3D plot, but I've plotted 2 of the incoming photon momenta. I mean, I've plotted the probability density in terms of 2 of the photon momenta, which are k1 and k2, and the third photon here of the probability density I'm showing here is actually a third photon that is emitted at delta r, right? So I'm only showing photons that have one of the photons re-emitted at the resonance frequency of the qubit, because that is what the qubit is going to spontaneously do. It's going to re-emit at its resonance frequency. So you can see that now there's a continuum between k1 and k2, so there's a freedom for the 2 photons that are being re-emitted. And that is what I'm basically, this can be understood like as this process where there's one photon coming in and 3 photon re-emitted. One at the resonance frequency here, delta R, and 2 basically with omega, one at omega and one at the remaining, at the surplus of energy. Okay, so this is why we have a continuum. The continuum is there because there's a freedom for this third photon momentum. Right, and this is what gives rise to this inelastic spectrum. Right, so that explains basically these photons. So that's, and this is a non-RW process. This is one of the interesting parts here. So this would all be encountered only using the counter-rotating terms of the spin boson model. Right. Yeah. So here, this is basically the kind of yeah. Okay, so what I wanted to show you is as I increase the coupling alpha, I can reach to a higher cross section. So you can see that the elastic spectrum here at low energy increases if I increase the coupling. So initially I was at 0.1. Now if I increase the coupling to 0.2 and 0.3, you can see that this increases a lot. So what I showed you in the previous plot, this was only the bottom, the red curve. That was for alpha equals 0.1. But if I go to alpha equals 0.2, then I get this, and if I go to the 0.3, then I get even more emission at low frequency. So, right, this is just the final part of my talk. I want to show, I want to calculate, these are calculations of the second order correlation function. So the idea is this is something that is easily measurable in, these are one of the typical measurements you could do in a lab which would prove, basically, which could demonstrate the presence of these 3 photon processes. So the idea of the G2 function is basically a probability of measuring a photon at time t plus tau, provided that 1 photon was already measured at times t, right? So the idea is the following, that initially, okay, I think I'm going to skip this part. This is not, that might be even not extremely clear. So if you look at the G2 function, okay, so in the output, so in the reflected signal, so you will see that basically if you had done an RWA simulation, so that supposing that we did not have the counter rotating terms in the simulation, then you would obtain a G2 function that looks like this, with which becomes 0 at tau equals 0. And that would be the typical G2 function if you have a current state being reflected on a 2-level quantum system. However, with my technique, what we obtain is that the actual G2 function is non-zero at time equals 0. And that is because actually if you only have rotating terms, the qubit can only absorb and re-emit 1 photon at a time. But if you have counter-rotating terms, you can have multiple photon emissions. And this way, you can actually measure multiple photons simultaneously. And that is why you will get an offset in the G2 function at time equals 0. So, so that would be one demonstration of these non-RWA photon processes.
So the expression for G2 is very similar to this out of time ordered. It's not exactly that, but it's almost that. And the behavior also seems similar-ish.
Out of time order, say it again.
Correlation.
Right.
This famous 4-point function that you study for scrambling,
right, of
information.
I think this would be that would be a 2-point function, right? The second order.
No, that's a 4-point function. That's a 4-point function. And the time ordering is similar to what you have. Actually, it should have been 80 plus tau, the last 2 things, instead of 80 plus tau 80. Mm-hmm. Then it would have been very, but the behavior seems very, very similar. It goes from 0 to 1, and in this way,
right.
And there is a sharp increase somewhere in between.
Right.
Yeah. Okay. This is quite interesting.
So I also wanted to show you that you can go, if you go to stronger coupling, this also, so again, with the RW, it's still 0, but with this technique I'm using, you can see that they are actually at time equal 0, the offset increases, showing that there's a bigger number of photons being emitted. Right. So okay, that's mostly it. I wanted to say that okay, there are some other interesting models to which I would like to apply the systems, in particular to the measurement protocol, because you can, in the measurement protocol, you drive the cavity with a qubit inside using a very strong drive. So it's a very closely classical drive. It's close to a classical drive, and the state of the cavity is quite classical. It's similar, I mean, close to a classical state. Therefore, it would be interesting to apply this current state expansion to this kind of dynamics, and this is one of the things that I am working on. All right.
Maybe we could end Nicola now so that we have some time for questions too.
Exactly. So that is fine. Yeah, this is just my conclusion. So now basically I just showed you, the first how this thing works using the rabi model, and then I moved on to show you a qubit waveguide QED kind of system where we scatter current state on the qubit. And so that's what I showed you, like so this elastic spectrum in particular at low energy in the second order correlation function. Thank you.
Thanks a lot, Nicola. It was a very interesting talk. Let's take some questions now. So I have a question actually. So it's a very beautiful formalism and all. But what about instead of using coherent states, you also enlarge it and use this minimum uncertainty states, like the ones which saturate this inequality, like you add this alpha A square plus A dagger square, and so you take into account quadratic fluctuations together. So
so you mean the squeeze states?
The squeeze states, yeah, exactly.
So
with A square, A dagger square, and also A dagger.
Squeeze one direction and one other direction is actually, so that's a very good point. Actually, there's work by our some competitors, especially, and I think it's this university in Canada. Ashish Clerk has some work exactly on looking at it's only on the ground state. They haven't done new dynamics. They've shown that they can use also squeeze state to describe the field state of the rabi model. So that is only for a single mode. They've looked at the ground state and everything, but yeah, these are things that can also be used to do that, to describe the field state.
Because naively speaking, if you include the quadratic fluctuation parameters, you also take into account the spread around a particular coherent state, because these are like the quadratic fluctuations around here.
Okay, so you're saying not the current state, only the current state, but also
like what I mean is that there is a general way to do this expansion where you can have the quadratic terms where you have A square, A dagger, and also the A and A dagger. So you can have all this, and they form some nice group structure, this whole thing. So there are, you could think about this. I think it's, there is this, I forgot, SL2R cross SU1, SU2 or something like that. I forgot the full, you could write it in a very nice, I forgot this, there's a general kind of theory of coherent states which takes into account this whole kind of structure.
Okay. So are these only the minimum uncertainty states, or are they, if you start adding these quadratic terms, you would actually start moving away from uncertainty?
Yeah, I think, okay, no, these are generally, if I remember, these are the minimum uncertainty states. Yeah, okay. We saturate this inequality, the most general states of this kind.
Okay. So all kinds of states that would satisfy.
All kinds of states that you can take and satisfy this. Yeah. And might be interesting, and in the sense that if you want to also study correlation functions and all, then probably it probably could help. Actually,
the expression for calculating the correlation function is very simple in terms of current states, because these are annihilation and the creation operator. So you basically, when I was showing you this current state, right? this G2 function. Right here you have a psi state. Basically, you're just applying A on the current state, so you just get a very simple expression, which I have not written here, but it's a simple expression just in terms of the different sum product of all the current states. Actually, yeah, it's interesting. There is yeah.
No, but you might need to add less number of states if you use this kind of, also take into account quadratic fluctuations already in the answers.
Yeah, you would have to include more states, probably.
Okay, but it's very interesting. The method seems to be very, very interesting, and so I also wanted to ask if you could compute something like the OTOC using this method.
Out
of yours, correlation.
Out of time.
Ordered correlation. Yes, something like 80 plus tau instead of 80 plus tau 80 in the last lines.
Yes, I think that would be possible. I think this would also be possible because here I can just choose basically exactly what part. So actually what I do, I have a simulation. At the end of the day, I have this current state that is a spatial current state. So this T is equivalent to a spatial part. So I can choose exactly where in this current state I'm applying the operators. So I think out of correlator would not be a problem. I would also be able to compute it in the same using the same simple expression.
Interesting.
Nicholas, is any of your code available on GitHub or anywhere else?
No, unfortunately, yes, I had, but it would be best for me to send it to you, myself.
Okay.
Definitely, if you are interested, I can send you my code. It is quite a big code, but I would be happy to to walk through the code and to include to explain to you how it works exactly.
Yeah, because I mean, this like general technique could be applied in a different context also.
Right. Yes.
Yeah. So. And your work is very, very, very beautiful.
Thank you. Thank you. There is something I want about coherent states I didn't have time to add, but the fact that there's a coherent state also allows us to solve this system very simply in terms of dynamical equations. So the equations scale as the number of modes in the system, which is quite impressive because if you imagine this very large system, it should actually scale as the square of the number of degrees of freedom. But actually, the coherent state allows us to find a very nice trick, which only allows us to solve the system linearly with number of modes. So it's not a problem to increase modes, at least to 1,000, 2,000. But yeah, that's the point I didn't really have time to spend time on. But there's something very funny happening, very interesting happening with the actual nature of the current states in the system, which allows this system to be solved efficiently.
Okay.
Excellent. Okay, so thanks, Nicolas, for the great talk, and thanks everybody for participating. So then see you around, and next week our speaker will be Hong Liu. He would be speaking on his recent work on emergent time in holography in quantum systems. So see you then next week. Bye.
Thanks.
Thank
Bye.
you. Thank you very much.
Bye.
Bye.
Hi, Nicolas. So if we can catch up sometime in the campus then.
Definitely. So actually, yeah, now that you reminded me, I'm actually only back in the evening tomorrow. So probably we will not be able to meet tomorrow. As you said, you're